When we're using polymer chains to stabilize a colloid, we need to know how big those chains are. So our measure of polymer chain size is going to be the radius of gyration. The reason for this is if we look at a polymer chain in solution, it folds back on itself. So there isn't really a specific size we can use, and so the radius of gyration is useful. What is the radius of gyration? Well, it just says that if we went to the center of mass and swung this polymer around, we rotated it, and then replaced it conceptually with a single mass on a string swinging around, that the two objects would have the same. So if we had a little ball of the same mass as the polymer coil and we swung it around, this radius here, r sub g, is the radius of gyration. So this object has the same moment of inertia as this object. Okay, so it's basically going to end up being a radius about like that. Not as far out as the farthest part of the polymer, but sort of part way out. Okay, so that's going to be a measure of how big a coil is, the radius of gyration. Great. Well, how are we going to figure this out since we've got this sort of random coil? Well, that's the model we're going to use, a random coil. So if we imagine that the molecule takes one step, another step, another step, and each of these steps are random, eventually we're going to draw out a random coil. Okay, so a random coil, these are really well characterized. We know a lot about them, so that's the model we're going to use. That's the model we'll start with. So for a random coil, the radius gyration is equal to the length of each step times the square root of the number of steps all over 6. And we do this, you might see this equation talked about as this is the length of the monomer and this is the degree of polymerization. I'd rather just avoid that entirely because what we're interested in is each independent link in the chain. And the monomer size is not really a good measure of the length of a chain because a monomer can be made up of many bonds and all those bonds might have free rotation. And so you want each step of the chain to be rigid. So we're going to use this as the length of a bond. And this will just be the number of bonds. That makes a lot more sense than using monomer length and degree of polymerization. Great. This gives us the size of a random coil. Let's do an example. So we want to calculate the radius gyration of polyethylene for a chain that has a molar mass of 14,000 grams per mole. And this will just give us a flavor of how big these coils can be. So we're going to set up a repeat unit, and note this is not the actual repeat unit for polyethylene, but we're going to use it because it's equivalent to one bond length. And we can see that if we have 1,000 of these, each one has a molar mass of 14 grams, and so if we have 1,000, we'll have 14,000 grams per mole. So that's what we've got. So we've got 1,000 bonds, and the length. Okay, so a single carbon-carbon single bond is about 0.15 nanometers. And so we're ready to go on this. So the radius of gyration is just the length of a bond, 0.15 nanometers. And then we have the square root of the number of bond lengths, roughly 1,000, all over 6. And that works out to 1.9 nanometers. There is something unphysical about the random coil model, and that's that it assumes the chain can cross through itself. In other words, it assumes that the links in the chains don't really occupy any volume. Now, of course, we know a chain can't cross itself. The solution to this problem is the self-avoiding walk. It's abbreviated. Usually the acronym SAW is used. So we're going to make a SAW coil. And this is a coil where it can't cross back over itself. And because the chains can't cross over each other because they take up space, that means that the coil has to expand to accommodate that volume that's excluded. And so it grows at a faster rate than the ideal coil. And so the exponent is not 1/2, it's 3/5. So this self-avoiding walk, or SAW coil, is going to be what we see when we have an ideal mixing between the solvent and the polymer. Ideal mixing, just to refresh your memory from thermodynamics, that means that the delta H of mixing is equal to 0. It's not endothermic or exothermic. So since energy is not released or absorbed by mixing, the process is going to be driven by entropy. So we can generate all that entropy when the polymer dissolves. So that's what drives this process. So if we have an ideal solution between our solvent or polymer, we get a self-avoiding walk coil, a SAW coil. So the polymer and the solvent form an ideal solution. A parameter that is used to characterize the interaction between the polymer and the solvent is the chi parameter. And another way of saying that the heat of mixing is equal to 0 is to say that chi is equal to 0. Because chi is a measure of how endothermic the mixing is between the polymer and the solvent. So in this case, it's not endothermic at all, and so the chi is equal to 0. So chi equals 0 means SAW coil. So whenever you see chi equals 0, you know that we're going to get a SAW coil. You might wonder if we ever see a random coil. Well, we do see the random coil when we have somewhat unfavorable mixing. It's when chi is equal to 1/2. That means we have endothermic mixing. So mixing between the polymer and the solvent is less soluble than an ideal solution, and that tends to contract the coil. So while the excluded volume effect tends to expand the coil, the unfavorable mixing tends to contract the coil, and those two effects exactly cancel, and we end up with a random coil. And just to refresh your memory, that means that the radius of gyration is equal to the length of each bond and then the number of bonds divided by 6. So it's a slightly smaller coil than we see with the self-avoiding walk. So those are the two situations you should be familiar with when chi is equal to 1/2 or when chi is equal to 0. This situation of having chi equal to 1/2 and therefore having a perfectly random coil, this is called the theta condition. And we would say that another way of saying this is that we say that the solvent is a theta solvent for that particular We'd also say that that's a theta solvent for that particular polymer. And because this interaction between the polymer and the solvent are temperature dependent, this is referred to as being at the theta temperature. So we might say benzene is a theta solvent for this particular polymer at this temperature. Now if chi gets much bigger than 1/2, what happens is the chain continues to contract, and at a certain point it just falls completely out of solution and we have an insoluble polymer.